I was going, I'm not sure I hit the record, and now I didn't hit the record. So we're in the GIFs folder, just so that we have that. But you've got a string or a wave in the lake, or a bob, a buoy that's bobbing up and down in the lake. And what you're seeing is the object move up and down. It has a maximum and it has a minimum and it has in the middle. And by watching the wave go through, you can see that pattern that hopefully we all recognize as a sine or a cosine. If I were to plot a cosine function, it's going to look like that curve that you're seeing. The sine function will do the same, and the only difference between the sine function and the cosine function is what we refer to as a phase angle. They're 90 degrees apart. And we'll see that a little bit more in our motion. So you see that you've got that bobbing up and down. We've got a maximum, we have a minimum. That's going to be related to the amplitude. And that's the amplitude is how big is that maximum or minimum. Then you can step to the next video or the next item. And you can see if I put that bob on a spring. And that spring, if we distort that spring or have that spring hang down, and in fact, I can kind of demonstrate it. I've got a spring here. I've got a spring, and I have the IO device that some of you used in Physics 1, and you see that it's just bobbing up and down. That is simple harmonic motion. There's a maximum height that gets up to, there's a minimum height, and then it bobs up and down. So we have that bobbing up and down. And it's a function of time. So one of the things that happened in Physics 1 is we didn't bring a whole lot of time into our motions. You know, we did velocity and we did acceleration, but we didn't have these functions of time. So we get to the maximum, we get to the minimum, and this is kind of that equilibrium point. So there's another one that you can go to, but this also shows you how I can have a different view of simple harmonic motion. So we have our bobbing mass on a spring, but look at what's happening to the green dot that it's traveling in a unit circle. It's also following simple harmonic motion. So examples of simple harmonic motion that you might find in the real world might be the filler tube on your tire. It's going to have the same behavior mathematically that my bobbing spring up and down does. It has that same behavior. A point on a wind turbine blade. The tip of the wind turbine, as it goes all the way around its circle, it's in simple harmonic motion because it's a constant going around in a circle. So that unit circle also is a really good example of simple harmonic motion. The third one, which we don't have here, if I were to put a pin on the end of my pendulum, or if you've ever seen a Foucault pendulum at a museum where it's drawing in the sand, it's going out and back, out and back. It has an amplitude, and it would draw, and if I had a piece of paper that I pulled it out like a strip recorder, it's going to give you that same sinusoidal motion or cosinusoidal motion. We're going to get that nice curve. So your first laboratory experience is, and by the way, I've provided you another set of information on simple harmonic motion. This is coming from the University of Colorado, and it goes through a lot of that. So you can print this off. It's just another version of what we're talking about, but you can print that off. So those gives you some visual pictures of what it is we're talking about in simple harmonic motion. A swing, which is going to act like a pendulum, a fan, a tire rotating around, something on a record player or CD player. You've got lots of examples of simple harmonic motion. So what I want you to do under this exploring physics in the real world, you're going to find simple harmonic motion in action in your environment. Get creative. The more creative, the better. Sometimes simple harmonic motion is in a very slow time period, and hopefully you can think of some things that are very slow. Sometimes they're very, very rapid. So if you're in chemistry and you look at the vibration between covalent bonds, that can be described as simple harmonic motion, because we can describe that bond as a spring system. And we're going to talk about that a little bit tonight. So you're going to go out, and if you'll open this up, you've got some examples. There's a crash course in physics. Your mission is to find and record 3 examples of simple harmonic motion. I would like for you to post those in the discussion board so that everybody can see them. And after tonight, you should be able to write the equation of motion for your example of simple harmonic motion. And that's what you will put in your PDF that you're going to submit. So this is going to be worth 1 lab. Your discussion board is half of the lab. The other half of the lab is your PDF. You're going to describe your example and why you think it's simple harmonic motion. You're going to provide the equation of motion in terms of the x, which is your amplitude, and we'll work through that today. So that's what you're doing for your simple harmonic motion. So that's the assignment there. This is where you're going to submit your PDF. And this is where you're going to put it in the discussion board. And the sooner you put things in the discussion board, the sooner people can respond to it, and it makes it a little bit better. And then I have a survey, because I want to see if you like the activity or not. So we do that. So that's your first lab. And that one does not need a laboratory memo. It just needs a PDF describing your motion and giving me your equation of motion. The other laboratory is the simple pendulum, and we will talk through that as we work through the lecture material today. But you also have a laboratory introduction that has everything in it except for the expansion. So if you had me last semester, this is the exact same lab, except we're adding 1 more layer of detail to it, and that's looking at the angle. And we only are doing it for 1 length. And we'll discuss that as we're coming through the material. So this lab is due on the 30th, and that gets you those there. We will talk about these other 2 later in the week, because they're more related to sound than they are simple harmonic motion. All right. I'm going to stop my share, and I'm going to start my share again. Okay, so just as a reminder, in the GIFs folder, it has those examples of the simple harmonic motion that we were just watching. This introduction is going to be a little bit more detailed than what we're covering tonight. And other lectures in the spring 2025 lectures are good. And then in the supplemental information and example problems, examples, those are just going to be there for extras in case you're getting stuck on something. Okay. So let's talk about our 3 models. So we have 3 models of simple harmonic motion. The first is our pendulum. And our pendulum will go a complete cycle, come back and forth. And if I were putting a pin on it, I'm going to get something that looks like this. We have our unit circle. And if I'm looking at it from the side, I'm also going to get a behavior that looks like this. And I have my spring situation where if I have my pin here, I'm going to get this going up and down and looking like that. So we've got our three models. That's our pendulum, our unit circle, and our spring system. Now, if I'm looking at this motion, this is position, and this is time. One complete cycle, this would be one complete cycle. And the time that it takes is equal to, we're going to use a big T, and we're going to call that the period. This is the amplitude. Okay, a lot of people will get a little bit confused. The amplitude comes from this equilibrium point, and that's going to be the amplitude. So A is going to equal amplitude. And this is going to give me my position is going to equal a function of time. And we're going to come back to that, but I wanted to start defining a few things. One is period, and one is amplitude, and we're going to define it. But we're going to start with this spring system, because we've seen this spring system before, except that spring system, we never really looked at it as a motion system, and now we're going to look at it as a motion system. So when we first looked at our spring system, we knew that if I had a spring, it was going to have an initial length. And if I put a mass on it, and we're going to give this a mass of 0.250 kilograms, and my new stretch would be some new stretch. And we used our Newton's second law. Which said mass times acceleration was equal to force. But then we said that with springs, we had something else, and we looked at it as Hooke's law. So this part is Hooke's law. And this part is the simplified form of Newton's second law. Okay. And we learned how to calculate. We can calculate this. So let's do that. We're going to start with an initial length. We're going to say that this is, we'll give it 30 centimeters. And our new length, we're going to say is 50 centimeters. Remember that X is equal to stretch. The negative tells you it comes as a restoring force. But we're just wanting to find the magnitude of K, so we're not going to have to worry about that direction, because this gives us direction. Because force is a vector. So we have to worry about that. But right now we're just trying to calculate our spring constant, and K was defined as our spring constant. And so we said, all right, we get mg is equal to our force, which is equal to our minus kx, but we're going to do magnitude, so I don't have to worry about the negative. I'm solving for k, so I get mg divided by x is going to give me k. My mass was 0.250 kilograms. Gravity is 9.81 meters per second squared. And my stretch is my 0.50 meters minus my 0.30 meters. And we can plug that into the calculator. And that gives us a spring constant of 12.3. On top, there are newtons. On the bottom are meters. And so we usually write our spring constant in terms of Newton meters. So we know how to calculate Hooke's law. We've done that before. So now we have a spring constant for this system. A couple other things we want to do is remind ourselves of energy. And our potential energy of a spring is 1/2 kx squared. Our kinetic energy is equal to 1/2 mv squared. And the reason we want to do that is because what we're about to do is do just like what we saw in that one diagram. So I'm going to start with my object up here. This will be at our equilibrium point. Then we've got a big stretch. We've got our equilibrium point here. And then we come back up to our little stretch here. So if I draw my curve that we've been talking about, and this is in relationship to time, so we're representing this as time. We're thinking about our spring bobbing up and down, but we're looking at this as my curve is moving in time. Here's my equilibrium point. This will be my amplitude. And since we played with our springs before, this is my amplitude on the other side. Okay, so we get it to bob up and down. Now, if I look at the total energy here, so we look at total energy, and the total energy of the system is going to be the potential energy of the spring plus the kinetic energy of the system. But the total energy, if I do this, this stretch is going to be my amplitude. My total energy of my system is going to be this right here. Then I'm going to get my 1/2 kx squared plus my 1/2 mv squared. And now I have my energy equation for anything that's happening in that curve, which is going to be really slick because now we can talk about how fast this bounces up and down. We can solve for velocity. So let's solve for velocity. If we do that, we're going to get 1/2 mv squared is equal to 1/2 ka squared minus 1/2 kx squared. My halves all go away. I'm going to get V squared is equal to K over M, A squared minus X squared. And if I go ahead and do the square root, I'm going to get plus or minus the square root of K M A squared minus X squared. Now, this is really interesting because I want you to look at this. K is dependent on the spring. M is dependent on the system. So how fast this is going to bob up and down is dependent on how we configure the system. And that's going to be really interesting as well. Let's go back. So this is a cool result. And the plus or minus tells you whether I'm on the way up or I'm on the way down. So we do have that direction. But let's look at our system here again. So we've got our spring that's bobbing, right? It's going to bounce up and down over a period here. We have mass times acceleration is equal to force, which is equal to our minus kx. Our acceleration is going to equal minus k over mx, again, dependent on the system. Which is a handy result. Now, we've demonstrated this using springs, but it's going to work for the same models up here. Whether I'm in a pendulum, a unit circle, or a spring system, it's just easier to describe this stuff using the spring because we can all picture it in our heads really easy. This is something we're all familiar with. If you've ever been to the bouncy ride at the park with those great big springs and you got the little kid on the ducky, you can have them go back and forth. You can have them go up and down. It's going to do the same thing, but the system is going to be dependent on the spring constant and the mass of my system, which is really an interesting result. And then we can take it back to our unit circle. So if we go back to our unit circle, if I have an object going around my unit circle, we talked about our angular velocity, and our angular velocity was equal to 2 pi times the frequency. And remember that frequency is also equal to 1 over the period. So I got 2 pi times the frequency. But this turns out, if I'm going around my complete circle, this also is related to my system. So my angular velocity is going to be related to my system. And now I can actually figure something out. So if we want to figure out for our system that we did, hang on, I want to make sure I got my pages numbered. We calculated, so we started with our system, our mass was 0.250 kilograms. Our spring constant, we calculated as 12.3 Newton meters. We can calculate the angular velocity of my system if I'm using it to represent this bead. Well, that's just going to be my K, 12.3 Newton meters divided by my kilograms. And that was my 0.250 kilograms. Take square root. Gives me 49.21 over seconds. So now if I do 2 pi, frequency is equal to 49.21 over seconds. Frequency is going to be 49.2 divided by 2 pi, 1 over seconds. Gives me 7.83. And remember, 1 over seconds is a hertz. And if I want to know the period, I have to flip it over. And this would be 0.127 or 128 seconds. So we can actually find out information about our systems if we know our spring constant and the mass that's in our system.
Can you explain the flipping over right quick?
Frequency is equal to 1 over the period.
Okay.
So the period's equal to 1 over the frequency.
Okay.
Yeah. All right. In the interest of time, and we have all kinds of fun stuff, remember that cosine of an angle plus 90 degrees is going to equal sine of the angle. So that's why we say that it's off by a phase angle. Okay, that's the phase. If I draw, so if I do this and I'm drawing this and I'm going to start here. This is just a reminder of how to work with sine and cosine. This right here, if I have this value, the value at 0, so at t is equal to 0, the value is going to equal cosine plus my phase angle. And this is going to be a phase angle. And that's just giving you your starting point. It's like where y sub 0 is, or where my bead starts on my circle, or where things are. Because I can move this reference point anywhere along the way. And if we're talking position here, so if I'm wanting to know the position versus time, my x is my position, or my y. You can do it either way. This can be x or y. But I can do position is going to equal the amplitude cosine omega t plus my phasing. So this is the generic position based off my cosine function. Okay. And so we can rewrite this as x is equal to a cosine omega t plus phi. This just gives us our initial start. And remember that omega is equal to 2 pi times my frequency. So I can also write this as x is equal to my amplitude cosine 2 pi my frequency times time. plus phi. And that's going to give me my equation for the position. So let's say I'm going to do an example. I have a clock. So this is x2, 2. This is 1, 2, 3. This is VI. And this is IX. I have a hand that's up here. And the hand has a length of, we're going to make it 5 centimeters. Okay. Its initial position we're going to make it a little easier on ourselves, is at 2. We're going to say is at 2. And the period for this, we're going to use the minute hand, is 60 minutes. Okay, so I've got the period, I have an initial position, and I have where the length is. So I need to know where I need to, first of all, let's find out at t is equal to 0. Well, so we got t is equal, let's do the amplitude first. Amplitude is going to be 5 centimeters because we're following this point around the circle. So the hand has 5 centimeters, so my amplitude is 5 centimeters. If I look at my position, so I'm going to take my 360 divided by 12. This is going to be 30 degrees, right? Because if I'm doing my cosine, that's 30 degrees. So my initial angle is going to be 30 degrees, but I'm going to want it in radians. And remember, 2 pi radians equals 360 degrees, or pi radians equals 180 degrees. So if I want 30 degrees, it's going to give me 0.523. So that's my phase angle. Now I need frequency. And I want frequency in 1/2 seconds. Well, frequency is 1/the period, but I got to convert that. So I got 1/60 minutes. And we know that 1 minute is 60 seconds. And this gives me 0.0000281/seconds. My equation is x is equal to a cosine 2 pi times my frequency times t plus my phase angle. A, we're given, I can write it as 5 centimeters. Cosine, I've got 2 pi times my 0.00028 times time plus my 0.523. So now I've got that written out. So I got 5 centimeters cosine 0.00174t plus 0.523 is my position equation. And that is exactly what you're going to do for your simple harmonic motion in the real world. I used a clock. I had the length of my amplitude. I had my starting position. I had the period. I went through and figured out what those equations or what those pieces of my equation are, and I plopped it right into my equation. Now, once you know the position equation, you can calculate velocity and acceleration pretty easily, because these are our equations of motion for this. I get A cosine 2 pi times the frequency times t plus my phase angle. I get velocity is equal to minus A omega sine 2 pi times the frequency times t plus my phase angle. And this is equal to minus A 2 pi my frequency, just so you see it written out. And then my acceleration and again, just writing it all the way out. And so these are our equations of motion. Now, so this is pretty cool. So let me give you a position. So I've given you the position equation. And I'm giving you that x is equal to 10 meters. So we're going to use a big object. 10 meters cosine 3 pi plus 0.6. I want to know the amplitude. I want to know the frequency. I want to know the angular frequency. I want to know the frequency. I want to know the period. And I want to know the phase angle. Well, this is easy. That's 10 meters because that's coming right from there. Omega, that's 3 pi. This is a little harder because that's omega divided by 2 pi is going to give me my frequency, because remember, omega is equal to 2 pi times my frequency. So if I do this, I get 3 pi divided by 2 pi. So my frequency is going to be 1.5. My period is going to be 1 over the frequency. So that's 1 over 1.5, or that's going to be 2/3, or 0.67. My phase angle, it's right here. So we can read right out of our equation, we can read a whole bunch of information for our system. You can read that right off of the equation. Now, just one more thing, we can do it a little differently too. So let's do this. So I'm going to give you a position versus time plot. This is going to be 0.5 meters. This is minus 0.5 meters. This is going to be 2 seconds. This is going to be 4 seconds. We want to write the position equation. Well, we know the position equation is x is equal to the amplitude cosine 2 pi times my frequency times time plus my phase angle. So at t equals 0, well, first of all, we know the amplitude is going to be 0.5 meters. So if I'm doing this, this is going to be 0.5 is equal to 0.5 cosine 0 plus my phase angle. So I get my 0.5 divided by my 0.5. That's going to equal 1, which is equal to the cosine of my phase angle. So my angle is going to equal the arc cosine of 1. And that's at 0. So my phase angle is 0. So we got our phase angle. The period, I'm going to read from the chart. And it's a complete cycle. I didn't mark it, so we'll do a complete cycle. This is going to be 6 seconds. That's going to, so t is equal to 6 seconds. So my frequency is 1 over t. So it's 1 over 6. .167. So now I have all the information to write out my equation. X is equal to 0.5 cosine 2 pi 0.167 t plus 0. And now I've read it right from the graph and I've gotten my equation. And once you know those components, you can plug them into the other equations because they're the same components for each one of those. Now, just as a reminder, when we look at our simple pendulum, our simple pendulum is going to go this way and back. And we know that t is equal to 2 pi times the square root of the length divided by gravity. The only way we get this through the small angle assumption. So for your lab, I want you to look at when your angle is approximately 10 degrees. I want you to look at when your angle is approximately 20 degrees. And then look at what happens when your angle gets like 30 or 40 degrees. I want you to watch what happens to the period. And this comes from the fact that I'm going to have things that are going to happen to my pendulum that get there. Now, for those of you who didn't go through physics 1 with me, what I'm expecting in the graph you're going to have to do t divided by 2 pi is equal to the square root of L over G. We're gonna square both sides, so I'm gonna get t squared 1 over 2 pi is equal to L over G. I'm going to get G divided by 2 pi t squared is equal to L. And if I look at this equation, so this is L is equal to G divided by 2 pi t squared. This has the same form as Y is equal to mx, which is a linear fit. So if I do a plot, this is length versus period squared. I'm going to get a best fit line. I'm going to get a slope. And my slope is going to equal gravity divided by 2 pi. So my slope, 2 pi times my slope, is going to give me gravity. And I'm going to do a percent error, which is my real minus measured divided by real times 100%. Make sure you're graphing this with the length on the Y and your period on the X. Use your units to figure out whether or not you're doing it correctly. But I'm also looking for, which is different than what we did last semester, I'm looking for you to look at the small angle assumption for your pendulum. So this is all part of the lab. All right. That gets us through simple harmonic motion. But I want to cover a couple of things on waves before we call it a day. So waves, first thing is they carry energy. Okay, they carry energy. We have two types. We have what's called a transverse wave. And the easy way to think of a transverse wave is to think of ripples in a pond. Vibrations on a string. A pulse down a string. I can look at a pulse and I can send this string with a pulse. Okay, I can send that string with a pulse and you'll see it move through. And that's a transverse wave. The other one, I need a slinky to kind of think about it. Because what's going to happen in your slinky as it goes through, I get compaction and rarefication and compaction and rarefication and compaction and rarefication. And these are called longitudinal waves. So transverse ones are easy to see. Longitudinals are a little more difficult. But my waves are going to carry energy. And I've got two types of waves. But these can be described by our equations of motion. That we've just worked on. Now, one other thing I want to talk about is if I send in a pulse and it comes in here, my pulse will reflect and it'll come back and it'll bounce off of my object. So I have waves that'll come in and I'll get reflection of my waves. They'll flip over and do fun things. But I wanted to introduce that idea about waves and then remind folks that the velocity of a wave is going to equal the frequency times the wavelength, or I have the frequency divided by the period. And these are in meters per second. So you get that you get this. We are going to start talking about mechanical waves. And so think of waves on a string. In a pond. Mechanical waves, they also have to have a medium. Meaning they have to have air, a string, wood, steel. They are going to travel through some type of medium. But they are going to carry energy. We have two types, and we can look at the velocity of the wave being frequency times the wavelength. And I am sure brains are now full. So I will open it up for questions.